Good evening, my name is Hector Atiaga. I am part of parallel number 2 of Electronic Applications in ESPOL. I'm a student of Electronic and Automation Engineering, and today we're gonna talk about microelectronics, in specific, the cascade current mirror configuration of transistors.
First of all, we're gonna look how a current mirror configuration is working. So here's the configuration of the circuit, and basically what we want to know if is how the load current acts with an current in the entrance of the circuit. Okay, so first we have to say if we have beta a very big number, then we're gonna know that beta plus 1 and beta plus 2 is gonna be similar to beta. So from there we have that the base current, this one right here, it's gonna be the emitter current divided by beta plus 1. That is almost the same as the current of the emitter divided by beta. Also, in this configuration we have two exact transistors, so therefore we can say that the voltage in the base emitter from both of them is going to be equal, and because of this we're going to have that the base current for those two transistors are going to be the same, and we're going to call it the base current. And as we can see here, if we have the same beta for the two transistors, because both of them are the same, then we have that the emitter, the current from the emitter 1 is going to be equal to the current from the emitter 2, and we're going to call it emitter current. So to make this analysis, we're going to do a Kirchhoff voltage law in here, as we can see right here, and we're gonna have that the entrance current is gonna be set by the alimentation voltage, the base emitter voltage, and the resistor in the entrance right here. Now we're gonna do a current Kirchhoff law in this point right here, and here we can see that the current of the entrance is entering, and the three currents that are going out are the collector current and the two bases current. As these two are the same, we're gonna say that this is gonna be 2 times the base current. So here we go, we have this equation right here, and from here we're gonna say that the current in the entrance is gonna be 2 times the base current plus the collector 1 current. This one right here, this small current right here that's entering the collector of the transistor. And doing some mathematics, we're gonna have that the current in the emitter, the one is going out of the transistor, is gonna be approximately the same that the current of the entrance. And as we said before, the current in the emitter 1 is gonna be the same as the current in the emitter 2. So, and as we can see right here, if we have beta really big, we know how to have that the collector current for both of them is going to be equal, and also the emitter current. So we can say that the emitter current 2 is going to be approximately the same that the collector current 2. And we can say, and also we have to know that the emitter current 2 is going to say the same as the load current. It's going to be right here, because we don't have any more cables right here. This current is the same as the one right here. And finally, we have that the load current is going to be the same as the emitter 2 current, and this current is the same as the entrance current. So finally we can show that this current mirror is working because the current in the load is approximately the same as the current in the entrance. Now that we know how current mirror works, we're gonna study this circuit right here that is a cascade current mirror with 4 transistors. So for the analysis, we're gonna say that all 4 transistors are gonna be the same. That what does that mean? That M1, M3, M2, M4, all of those transistors are gonna have the same voltage overload. So in this exercise, what we wanna know is the output resistance. Why do we wanna know that? Because as we know, these configurations uh, permits us to increase the resistance output. So to to measure the resistance, we know that the resistance is gonna be the voltage divided by the current. So we're gonna here is gonna be our resistance output. So we're gonna put right here at a voltage like a battery, so we can do our math. So it's gonna be right here, and this voltage source is gonna have an output current, and these two things is what we're gonna have to find. So as we can see right here, this is a lower frequency low frequency equivalent of these 2 transistors, because we want to know the resistance output, so there's no point of analyzing these transistors. So in these transistors we have these are the equivalents. We have the resistance of the transistor 4, the transistor 2, and the dependent current source for both of them, and the open gate, right? So from here we go through here, and as we can see here, the current of the source is gonna be this right here, this equation right here. And finally, if we do some math, and we're gonna found this term right here, this one right here, that's gonna be our output resistance. And as we can see here, this is our final equation. And as we know, because we're working with the same transistors for all 4 of them, we can say that all resistance output for each resistor is going to be the same, and also that GM4 multiplied by the resistance of the transistor 2 is going to be much higher than 1. So finally, from all this circuit, doing a little bit of math, we're gonna have the final equation for the resistance output for a cascade current mirror circuit. That's gonna be governed by the GM4. It's gonna be the parameters of this transistor multiplied uh, by the square, by the 2 times, multiplied 2 times by the resistance output of the transistor number 2. And that's it.
There are some advantages and disadvantages in using the Cascade configuration with the current mirror devices. Two of the main advantages are they increase the resistance output considerably, and also they totally suppress the effect of channel length modulation. And the disadvantages of using this configuration is that, as if it's a very more complex configuration, the analysis of its own it's going to be very more difficult, and we're going to have to study it in depth in order to make the configuration we want, in order to make the transistors have the function that we want it to have. Thank you.